So welcome to CC Colloquium for March 16th, 2022. We are now operating under ASU's slightly more relaxed COVID rules that don't require masking in our auditoriums and such. And it's nice to see a nice audience here. First time in 2 years, I actually had to go in the lobby and usher people in here, herd them into the rooms. That's awesome. This is the first of a series now of presentations we're going to have in person. We have a couple of other visitors coming to town. Brent Sherwood next week. Kelsey Johnson is coming in a few weeks after that. Also, she's planning to come in person. We have presentations by a couple of our postdocs and at least 3 of our graduate students. At least some of those are going to be in person. So we're going to start making more use of the auditorium. So Rick, you're on call. Announcements. I think the only announcement is that Sun Devil Giving Day is tomorrow, and Kim tells me that free donuts will be available in the CC lobby in the morning for those who come by and decide to give using the computer terminals that are there. So Sun Devil Giving Day tomorrow morning, or tomorrow all day, but free donuts as a bribe, as an inducement, an incentive in the morning. Incentive. Yeah, so Kim says, please, if you do give, please give to CC and to any of the scholarships that support our students would be greatly appreciated. And so with that, I'm going to turn it over to Sanj to introduce our speaker.
All right, so it's my great pleasure to introduce Professor Sarah Tuttle, who is our speaker today, and tell you a little bit about her. So Professor Tuttle is an instrumental astrophysicist, so it's like 2 scientists in one. She builds instruments and studies galaxies. And her specialty is that she is one of the few people who actually working dedicatedly to build instruments that are able to detect very faint gas around galaxies. And that's very interesting because that's kind of fundamental to understanding how galaxies evolve. A little bit of background, Professor Tuttle started her journey in astrophysics as an undergraduate student in the University of California, Santa Cruz, graduated in 2001. Then she went on to get her PhD from Columbia University in 2010. After that, she was a postdoc at UT Austin working on the virus spectrograph, which is now in McConnell Observatory. And then she is currently now at the University of Washington from 2016 onwards as a professor, where she is continuing the great work of building exciting instruments and studying galaxies. But she's going to tell us more. So, to start.
All right, thank you so much, Sanj. All right, feeling brave, you're all far away. So as we discussed, some of you came to the coffee talk earlier, so this is going to be mostly an astronomy talk, but anyone who wants to talk instruments, feel free to ask questions or to interrupt or to come up afterwards, and we can talk more instruments. This is in fact a channel from the virus spectrograph. Early days, this was one of the prototypes that we made. And so my engineer and I are taking a very scientific picture because we were so excited we actually got it assembled. All right, so first of all, just as a reminder, since we haven't done this for a long time, so long actually that it was pointed out to me as I set up my slides that I had 2020 in the corner. So that's how long it's been for me. And there we go. So I don't know what the rules are in your auditorium, but as a reminder, do what you need to do. If you need to get up or stretch or something comes up, you should do that. These chairs are not always comfortable. Feel free to stand up. I'm not like surveying you from the front here. So first, I just want to get you excited about studying galaxies and gas. I'm excited to be here because I know many of you are already interested in that topic, so that helps a lot. But I just want to kind of give you a brief overview. What are we talking about and why is this a topic that so many of us are now very excited about? If this is not necessarily your neck of the woods, here are some acronyms I'm going to be using. The circumgalactic medium, the intergalactic medium, the intercluster medium, warm, hot intergalactic medium, really like so many words, just be like, oh, warm, hot, diffuse gas in places. It's really all of that. And of course, we'll be talking about Lyman alpha So Lyman alpha emission is neutral hydrogen emitting between first and second transitions. And relevant for the very end of this talk, at rest wavelengths, it's down in the far UV at 1216 angstroms. So just to orient you on our very largest scales, this is our universal energy budget. So all the budget in the entire universe, when we add it up in a pretty general way, most of the energy is dark energy. We will only talk very briefly about dark energy since this is the experiment that we're using data from, is made to be a dark energy measurement machine. Almost 30% is dark matter. So that's fantastic. And that leaves us about 5% for otters and everything else. Right? So everything that you usually interact with in your day-to-day is primarily not what the universe is made of, but luckily, we'll get to the otters sooner or later. If we zoom in on that 5%, we find insufficient otters here as well. Primarily the universe, when we talk about baryons, is just made up of gas. So we've got some cold gas, we've got some photoionized gas, some warm gas. Galaxies are only like 7%, so a paltry amount. But we talk an awful lot about galaxies and not nearly as much about the gas here. And this is from old work from Mike Schall. So we're thinking about gas, we're thinking about galaxies, and a lot of it just comes down to connecting our large cosmological scales to the human and otter-sized scales that we care about. So this is a cold dark matter simulation, and we see here that when we simulate what's happening in the universe from early times, we see these condensations into filaments, often called the cosmic web. And in the densest part of these filaments, we see formation of things like galaxy clusters and galaxies themselves. So when we look at, say, dark matter and dark energy, we see kind of baryons condensing along these tracks, right? And so when we talk about studying galaxies, we can study them for their own sake, and we can study them to try to tie back into the cosmic web and all the way back to kind of the initial origins of the universe. Galaxies, of course, are popular to observe because we can. So as the old joke goes, you look for things that you can see in places you can see them. So we always kind of have that inherent observational bias, but we can see a lot of galaxies. There was just a picture from JWST today looking at galaxies. This is exciting. And so we can observe galaxies relatively easily, right? When I talk about observing dark energy, as we see later, kind of a pain. I'm not going to lie, it's not an easy thing to observe. We see its impact. But when we talk about galaxies, we're able to observe them through many pieces of cosmic time and many stages of evolution. And we're also able to observe a variety of processes that happen. Although galaxy timescales are much, much longer than human timescales, because we have such a large sample of galaxies, even in this small image, we're able to see star formation, the quenching of star formation, mergers and interactions throughout all different phases. We can see inflows and outflows, mostly outflows, maybe some inflows, and even turbulent interactions. So from the scales of stars that form in our own galaxy, all the way to kind of galaxies that are interacting and merging, even at higher redshifts, we're really able to observe the physics in many different stages. Now, when I talk about the CGM, for those of us who went to graduate school a little longer ago, the CGM is brand new. Now we talk about it all the time. It's like it's been with us forever, but the circumgalactic medium really is only a phrase or an idea that has been with us for something just over a decade. In general, we talked about the intergalactic medium. So this is the diffuse gas that is kind of filling the space between galaxies, outside of clusters, outside of groups. This is that gas that's following those filaments. And it's kind of the part that got left behind as galaxies form. So it's relatively pristine gas out here. The galaxies, of course, have lots of metallicity. They're throwing gas out of themselves. They've got maybe outflows happening here. And so over time, as we looked at simulations and also kind of started to discover more about these processes near the outskirts of galaxies, it became clear that there was probably a regime of the intergalactic medium that was different, right? Where we were having a lot of these smaller scale processes, kind of an interface between the relatively pristine gas that's in the intergalactic medium and kind of the really messy and ongoing drama that's happening in the galaxy. So there's a circumgalactic medium that's surrounding it and is in some way coupled to galaxies. So here indicated by these outflows. The CGM has been probably best studied through background quasars. So in this case, you have a background source. It can also be a galaxy, but quasars are bright. We like that, and this gas is faint and hot. And so you have a single pencil beam that cuts through the CGM of a galaxy. We have done, I won't talk today, but we have done kind of looking for the intergalactic medium in emission. And it's tricky because we don't know where it is and it's very faint. But we do have a proposed experiment that I'll tell you about at the end of this talk, where we have a lot more information now as these surveys are kind of finding more and more information about the CGM in different locations. We can start to really target it and try to better understand what this morphology looks like and what processes are happening in the CGM. So I'm going to start off with these kind of very vague questions. I'm going to show you some really new, so ask lots of questions because I will not have answers, but some exciting new results from some of my graduate students. And then I'm going to show you a new proposed project that we have kind of relatively recently submitted. But these questions are kind of what's driving me as we think about what questions to work on next and try to understand what is happening on this interface between large and small scales. So first, there's kind of this ongoing question in galaxy evolution about how do galaxies interact with their environment? Now, often we think about their environment like, are they in a cluster or are they in a group? But in this sense, I'm also thinking about the CGM and IGM as well as other galaxies. So kind of what are those external processes that might be happening? We're also trying to understand how those interactions change galaxies, and in particular, what they might leave behind so we can figure out what has happened to a galaxy in its lifetime. So galaxies, in fact, have lots of changes over time. They're impacted. Even when we look at the Milky Way, we see stellar streams that tell us we've accreted, are accreting smaller galaxies. And so really, since we can't usually catch them in the act of whatever interaction is happening, we need to figure out what's left behind, right? What are the indicators that tell us what happened? And then, of course, there's this evolution, right? Do these effects vary with cosmic time? Are things more likely or less likely? Or do they leave kind of different imprints on the galaxies? In terms of the CGM, we're going to go with the very big question of like, what is actually happening in the CGM, right? We have a lot of cartoons for what might be happening, but is it right? We had this artist version that has this kind of smooth halo with like this just magically transitions from the galaxy. Is it homogeneous? Is it spherical? Is it chunky or smooth? We have some answers. It's probably not peanut butter, but you never know. Does that evolve with time, right? Does the relationship between the CGM and the galaxy evolve? You can imagine that maybe there's less gas, maybe galaxies are accreting most of what's nearby, and so it kind of gets decoupled. And in particular, what are the dependencies? So is the CGM dependent on galaxy conditions? Probably yes, but also are galaxy conditions dependent on the CGM, right? And kind of who's driving this bus and what's that exchange look like? So first I want to talk about some results we have from data with the Habitable Telescope Dark Energy Experiment. Should be able to say it because I've said it 1,000 times now. HETDEX is a project that was truly designed to try and measure dark energy between a redshift of about 2 and about 4. We're using it to look for Lyman alpha halos. We're using the data, and the survey is about 50% underway right now. So I'll show you a basic outline of the experiment and the telescope of the instrument, and then we'll look at some of the results that we have. So this is the design, the survey design and experiment design. The idea here is to use Lyman alpha emitters. So Lyman alpha emitters are relatively small but high star-forming galaxies at higher redshifts. We're kind of using them. See, my weirdest analogy is, those light nets people use them like at the holidays. They throw them over bushes. There's like a whole bunch of either LEDs or standard bulbs, and they're in the kind of weird stretchy net, and they just change shape with whatever you throw them over. So we're using Lyman alpha emitters like those weird nets. So the Lyman alpha emitters are bright. We can measure them. And we're using the actual distortion, so looking at their distribution and looking at distortions in different directions in space-time to put constraints on dark energy. We need we're trying to make a relatively strong constraint, trying to get down to a percent accuracy at redshift greater than 2. And in particular, we're kind of working in these relatively, these are kind of the ranges where HETEX is able to contribute the most. I also think that the range we're working at, for me, is kind of interesting because redshifts between 2 and 4 is really the peak of star formation. So these are galaxies where there's just a lot of change happening in the universe. We know that kind of the conditions are different from our conditions now. So this is an interesting place for us to get to sample, what is happening out there. So besides measuring dark energy, which is exciting, we also end up with these huge catalogs. The HETEX project is not a pointed survey. So we have an area that we're surveying. We don't know what we're going to get. We have to be able to actually decide what's a Lyman alpha emitter, right? What's a local galaxy? What's a star? So this is the projected catalog. Again, we're probably about halfway there. But as with everything, we're refining as we go. So the expectation is to get something close to 1 million Lyman alpha emitters. The area that we're surveying is 9 cubic gigaparsecs, although that area is not fully filled because of the experiment design and the approach. And our redshifts are between 1.9 and 3.5. We do catch a few things. That's kind of our reliable redshift range. We get a little more on the edges, but in general, that's not something we're using for like our cosmology results. We also expect to get something like 600,000 O2 emitters. These are our biggest contaminants, although we have people on the team who are using them for science. These are kind of the low redshift galaxies. They're at a redshift of about 0.5. And these are the things that, because of the design of HETEX, our spectrographs are low resolution. So these, when you catch either O2 at 0.5 or Lyman alpha at 2.5, they basically look the same. So we also use imaging surveys and other ways to differentiate between low redshift and high redshift sources. We also get a lot of other things, hundreds of thousands of other galaxies, hundreds of thousands of stars. One of our first papers was about novel white dwarf discovery, which is exciting, galaxy groups and clusters, and even resolved kinematics with about 5,000 local galaxies. So the catalog is really, really broad and something that we'll be using for years, kind of going back to the data. Again, this is kind of, all of this is extra, right? Because the dark energy science kind of got us started. Inevitably, I'm excited about the hardware because I built many of the spectrographs. This is just to give you a quick overview. So the way that HETEX works, it's a little bit unusual. The Hobby-Eberly telescope does not point from the primary. So the primary is a 10-meter segmented mirror. The mirrors themselves here are 0.9 meters. But actually, what's moving is the secondary system. And one of the parts of the project as we got ready for HETEX was actually we had to rebuild this entire system because the optics required for the upgraded field of view, we increased the field of view by a factor of several. It's basically the size of the full moon now on sky. The optics were too heavy for the current system. And so the optomechanical design is entirely new here. The focal plane feeds just under 35,000 fiber optics. Those run down the side of the telescope. This is a CAD model because you can't take the dome off of the telescope, and this is the easiest way to see it. These big green kind of worms are fiber optics. It turns out that 35,000 fibers, even though the fibers are skinny, weighs a lot. So you have to be, you have to route those carefully, and then they go into the banks of spectrographs along the side. This is what the focal plane looks like. This is not quite fully filled. Because HETEX doesn't have all of the time on the telescope, we do leave several slots open in the center. This is the Habitable Planet Finder. These are 2 different channels for LRS2. This is a low resolution spectrograph, although actually it's higher resolution than virus. And this is a spectrograph pair that we built in the virus mechanics, but with different optics to improve our spectral resolution. We can also do follow-up with that instrument. This is an individual fiber bundle. So one of these is about 500 fibers, and it feeds 1 unit, which is 2 channels of the spectrograph. And so you can see them here in the focal plane. Here's us installing spectrographs. I just can't not show you because it was exciting and sort of terrifying. So we bring them up to the mountain, pump them down one last time, install them in these tall cabinets. So these are kind of facing the outside, although they get covered up. And then this is kind of facing, the mirror is to this side. So the fiber optics come down and then are fed into the cabinet to feed the spectrographs. We had to wear hard hats and climb up and down in JLGs. Always exciting to do things in large. So again, these Lyman alpha emitters are really our measures, our probes for het decks. But for the work that I'm going to show you here, we're really curious about the LAEs and their environments, and in particular, how they might illuminate gas that surrounds them. So we're working with and this is work done by my graduate student, Brianna Thomas. She's working from kind of one of our first stable sets of catalogs. It has almost 600,000 objects, but most of those are not LAEs. Many of them we're sort of still in the process of doing a lot of sorting. And for this work, we made a variety of cuts, both to ensure that we were getting LAEs, but also to try to kind of get our surest things. So over time, this work will be repeated as the sample grows, as we're able to kind of probe different spaces. But right now, just so you have some context, first of all, the important thing, we required that the preliminary classification be a Lyman alpha emitter. So it is possible that there are more Lyman alpha emitters in there for us to pull out, and we have a variety of ways that the team is going through and kind of checking those. But for this work, it was adequate for us to be like, be a Lyman alpha emitter. We don't need to have all of them. We just would like a sufficient number. We go for high signal to noise. So this cut, you can move up and down. Most of these, we experimented with the range a little bit to make sure we were kind of getting the data we felt the most secure about as things like the pipeline settle down. We trimmed it just a little bit. So the seeing at HET can be okay, and we kind of observe in many conditions, but especially because we were looking for extended emission, we didn't want to be in kind of a high seeing situation. So we limited this to 1.2 to 2.0. In general, I want to say the average sight seeing for our observations is about 1.5. So this is not a ridiculous cut. Once we kind of get much higher than this, it just gets it gets too big. The objects are too small. And then what else? Oh, and we also wanted to make sure, because we wanted to look explicitly at evolution as a function of redshift, we wanted to make sure we had pretty high confidence in the redshifts there, right? One of the ways that we have higher confidence, so we do see Lyman alpha emission lines, especially in the brighter sources. You often get multiple other lines to make it easier to confirm the redshift. And again, we're working from 1.9 to 3.5. So when we make these cuts on this original database, we come out with just under 8,000 Lyman alpha emitters. I'm going to pause and emphasize that it's a lot. We will have many, many more, but when I show you some of our results, we're comparing them to other work that has been done in this field, and the size of those comparisons are often like 10 or maybe like 35. So it's been really difficult to get large sample size for this kind of work, and so we're really excited to have the opportunity to work with just big enough samples that we can start to look at them as subpopulations and really look at how they might be changing. So I will show you a little bit of the beginning there, but we were pretty excited to get kind of close to almost 8,000 galaxies. Felt like a really good starting place. Just to give you some idea of what kind of confidence we have, or what do we think is happening here. The technique that Brianna used was to actually use the spectra, the data cube, to make Lyman alpha images. Then she stacked the images, and we looked for extended emission. You can see here, we're just kind of showing that the median surface brightness profile here is in blue, and the PSF is in black. So we're seeing sort of well clear. Something to keep in mind here, and this is a Bootstrap median error. The error kind of does go up as you get further out in this particular technique. We have a collaborator in HetDex who used a different technique and a much narrower set of samples, like a kind of the gold standard sample. That paper just came out on the archive, and she was able to go much further out and is also seeing emissions. So we're consistent with that work, but because of this approach, we're really probing kind of the inner region, which I would say is like on the cusp of the CGM, perhaps. So these are surface brightness images. They are stacked as a function of redshift, and so our lowest redshift bin is here, the highest redshift bin is here. If your eyes are very sharp, although luckily the screen is really big and you're not too far away, you can see the numbers in each bin here in the corner. So we've got a pretty reasonable number here, even in our highest redshift bin of a few hundred. So the PSF, so you can see kind of one of the things we're working with, the PSF is not small compared to the galaxy. And I'll talk a little bit at the end, but one of our next steps for this work is to do some modeling work to be able to really remove the galaxy light, to be able to identify and remove the galaxy light, to kind of differentiate between the core of the galaxy and any sort of extended emission. But here, certainly, I think it's pretty straightforward. You can see extended emission in all of these stacks to varying degrees and varying amounts of smoothness. This is kind of the edge on stacks. So to orient you, again, we're looking pretty similarly here, right? We've got the number, the redshift bin, and this is our high redshift, so we're kind of doing this. The PSF now is a dotted black line, and the surface brightness limit is this dotted red or hashed red line. And so all of our data from the stack kind of in each point. So now we're looking at individual data points moving out from the center of the source are these teal dots. So I think our current argument is, and we're working a little bit on some of these errors, but our current argument is this is an exponential fit to the data points, that teal line. We're seeing pretty repeatable exponential fits, except in a few of our samples. Some of them are really, really good. Some of them are a little bit weird. And so, this is pretty consistent. As we do, we have sort of a variety of slices. This is as a function of redshift. We're looking also, for example, at equivalent width and a few other different cuts. But pretty repeatably, we are seeing that kind of no matter how you slice it, we're seeing this extended emission well past the PSF and kind of moving into the future, and not even in many cases approaching the surface brightness limit of what we're able to measure there. This is kind of maybe my favorite plot, partially because I think it's very aesthetically pleasing, but also because I think it's interesting. So this is a comparison. At the bottom here, we have redshift, again, between 2 and 4. And here we have the scaling from kiloparsecs. So this is useful because we're really able to compare directly with much of the work that's been done in this field so far. You'll notice Chuck Spiedel's points up here. These are really high luminosity Lyman break galaxies. I have one plot where maybe we can see if we think that they're kind of comparable. But there's a lot of reasons why this study is pretty different from everything else that you see here. So I think in general, we see that we're fairly consistent with what other groups are measuring. And something that I'm excited about, but we're still kind of looking into, because again, still in prep, I really like this step. It's exciting. I don't know, is something happening there? So it's interesting. It's not quite straight. It's not like wild evolution, right? We're not seeing like huge changes, but certainly I would argue that like this step looks pretty real to me. And this kind of dip looks pretty real to me. So we're doing a little more following up, and as we are able to, we'll add more sources. But it looks like, although I, again, would not say that there is a huge evolution, it does look like that perhaps as a function of redshift, we do have some change in terms of what's happening in the gas surrounding these Lyman alpha emitters. And so you can also see, I should say, at each redshift, the purple diamonds are kind of the sum of all the teal diamonds. And so the subsamples are underneath. You can see some of them kind of have a little bit more spread. And then these are I think they're medians. So anyway, I think this is it's exciting. We'll see. This is the thing where I'm like, let's see where this goes. What do we believe about that? This is looking again at our sample. So teal are the subsamples, magenta are the combined samples. And so this is the scale length on the y-axis. Here we have the Lyman alpha luminosity, and here we have the equivalent width. Again, and these are those checkpoints up here. So I've mixed feelings about how this could go, and I'm hoping we can fill in some of the space here. You can, if you're very professional and just use like a line in Keynote, try like fairly convincing line here, right? Like it's not ridiculous. Or you could just be like, I don't know, this is shenanigans. These are kind of the choices you have probably in this plot. Certainly R points, I would say there's not like a very strong relationship here. But I might make some argument that you see some reduction of scale length as a function of your luminosity here. This seems like a mess to me. I feel like this is a plot where someone would be like, as you can see from this very obvious relationship. Like, no, I do not think there's an obvious relationship here. Again, with some of the subsamples, you can make some arguments, but it's a bit of a mess, if I'm honest. So, we'll see what keeps happening. But here, I'm kind of pulling for a weird line here. We'll imagine our very professionally drawn straight line. I almost put a line on it, and then I decided that you deserve better. All right, so now I'm going to change mode. So again, this is redshift. The HETEX work is at redshifts, between 1.9 and 3.5. I'm going to change modes and look at a galaxy set that we have that is between a redshift of about 0.003 and 0.05. So these are much closer galaxies. And these were interesting because this set of galaxies came up in an attempt, working with a colleague, Stephanie Tonophin. We were trying to find ram pressure stripped galaxies. And so this is an example of how you can totally fail to do the thing you're trying to do, but keep beating away at it in the off chance that you learn something interesting about galaxies anyway. Oh no, not that. Oh. You've given me too many buttons. I have too much power. So for folks who don't look at galaxies very often, how do we classify galaxies? We tend to use what we call the Hubble tuning fork. I don't know. It has a place in my heart because we've learned it so many times, but I think it's less and less useful over time. Over here, we have kind of bluish, spiralish things. Over here, we have blobby red things. These are old. These are young. In general, when we look at this, we're really looking primarily at stellar age. So these are optical colors. And what we're really seeing is kind of what color are the stars in a particular part of the galaxy, or if we look at a whole galaxy, kind of overwhelming that galaxy. As we've gotten better data, of course, we can kind of see chunks of stars, red and blue stars in different areas. But when we think about color, we're really talking about optical color. We're talking about stellar age. But of course, then we get punchy and we start looking in multiple wavebands. And so this is from SINGS. This is Spitzer infrared Hubble tuning fork. Things already are getting wild out here, right? Suddenly this blue and red thing is just like not telling us the same at all. But here we can still see, right, we have ellipticals, not doing nearly as much as you might hope, but we still see, strong spiral arms or bars. Then we can up the ante and look in the ultraviolet. Here, of course, when we're looking at blue and red, we're actually looking at far UV and near UV. This is telling us, again, about ages of stars and star formation rates. Amongst other things, we get some really spectacular morphologies here. Of course, in the infrared, at least in some cases, we're exposing what's happening behind dust in a way that the ultraviolet is vulnerable to. So, we start to open up the dimensions as we start to look in different band passes. So I show you this not to just flash a bunch of pretty pictures, but as we look at our breakbird galaxies, we'll start in the optical and then look a little bit at many of the other ways that we can understand the underlying traits of galaxies. So the breakbirds themselves came from a parent sample by Lackner and Gunn. This sample was meant to do bulge disk decomposition that was physically motivated. So we always go back and forth in astronomy. Sometimes we're like, I found this really cool tool in economics. I can use it. Totally, that's going to explain galaxies. And then sometimes we're like, surely we should ground ourselves in physics because that's how the world works. Let's try that. It turns out sometimes they both work or they work differently well. And so the idea was to try and find ram pressure strip galaxies because there already was a significant chunk of galaxies. This is about 70,000 galaxies They're from the Sloan Digital Sky Survey Imaging Survey. And when we make these cuts, and they're face on to do bulge disk decomposition. And we make these cuts to kind of identify some star-forming galaxies. So we want them to be face on. We want them to be kind of physical. This is really just a physical color cut that gets rid of weird things that have popped into the catalog. They're low redshift, and they're pretty bright. When we make, and they're star-forming, sorry. Using DN4000, which we can talk about if that really means star-forming, but we'll call it a star-forming proxy, for lack of a better term. This gives us about 4,000 galaxies. And then we split them into 4 categories. So we split them into things with a blue bulge and a blue disk, things with a red bulge and a red disk, sort of standard spirals, and things with red bulges and blue disks, which is mostly what we think about when we think about sort of your generic spiral galaxy. Then we also had a category for blue bulges and red disks. And so those are the breakbirds. The idea was that if we looked for things that were star-forming in their bulges, but their disks were red, that we might find things where the gas had been removed from the disk, which had terminated star formation. We thought that we were feeling pretty clever. It felt good. So this is just an example kind of how that worked. So this is DN4000. I will say that I'm doing a terrible thing here. I do not recommend this. I'm mixing a whole lot of things here, and you should like keep your eye on the ball between as I move it between the cups. Some things are fiber measurements. The fiber measurements for Sloan are measuring the centers of galaxies. Some things like color are from the imaging data. In a minute, I'm going to introduce you to manga data, which is integral fibers, so fibers from across the galaxies. And some stuff we have is a combination of fiber and imaging, and some of the value-added catalog. I apologize, astronomers of shenanigans. So here's the DN4000, and here's the color of the disk. The underlying sample is showing you what's happening in the current sample. Depending on if you like looking at things in these dimensions or you love histograms, you can choose your poison. So these are star formers. They're represented by this blue histogram here. These are quiescent galaxies, red histograms, and the breakbird sample is here in green. So we're in that star forming region, but we are kind of in this red disk area. Oh, sorry, and it's 126 galaxies. That seems important. So out of like 4,500 galaxies, only 126 fell into this kind of weirdo category. Okay, in many ways, these galaxies are really average, kind of boringly so. This is what some people call the galaxy main sequence. We have the mass here on the bottom. We have the optical colors here. So the breakbirds, again, are plotted on top of the current sample. So primarily, they're living in the blue cloud, sort of where star formation happens, as well as the green valley, if you here sneak over to the red sequence, right? But these sort of look like star forming or transitional galaxies. For those of you who don't think a lot about galaxy evolution, the green valley is I would say complicated, but not really, just a complex place in the sense that we don't really know what's happening here. We don't know if galaxies are like on vacation in the green valley and want to come back to the blue cloud. Maybe they're on their way to the red sequence. Not really clear. So when we talk about this as the galaxy main sequence, I would argue like stars know what they're doing. Galaxies are like a whole lot of rats tied together. So we should be a little careful with our analogies there. When we look at them in the near UV, these galaxies are star forming. The caveat here, this is GALAX data. So GALAX data is integrated over the whole, it's imaging, it's integrated over the whole galaxy. And the trick is that not all of many, I mean, you can see there's lots of dots, not 126, you don't have to count them. But many of them are detected, and the ones that are detected are pretty clearly star forming. Not that surprising, because to get detected with GALAX, you probably need to be star forming, or at least have some star formation in the galaxy. This does not tell us, though, about if it's happening in the bulge or the disk. It's just kind of for the whole galaxy. And when we use Ys in the infrared with 2 different sets of diagnostics here, this is 4.6 minus 12 and compared to 3.4 minus 4.6. and this is as a function of mass. Again, we're very firmly, those that are detected in the infrared are very firmly detected in the star forming region. So these galaxies are definitely forming stars. WISE, again, is imaging, so we're talking about across the whole galaxy. There's enough star formation that it's coming through as a star former. Here was the thing where we were like, oh no. So we actually have a variety of environmental plots. This one is row 5. I'm not going to make you, oh, sorry, sigma 5. I'm not going to make you look at all of them because they all tell you the same thing in different ways. Basically, this is just the distance from the group center. Being straightforward. Group is defined really loosely. It's kind of like, how close is this to any other thing? And what you might have expected or hoped to see was that obviously these galaxies are a little bit funny. They've lost a bunch of gas and they're probably all really close to other galaxies. They've got lots of friends and they're in really dense environments. And it turns out that hypothesis is wrong. It's just wrong. We were wrong. It was sad. It wasn't really sad. It was exciting because we got to think about new things, but it was definitely surprising. I will also say, just because I like, misery loves company, we found out as we talked to people about these galaxies, there was a whole other team at Princeton that had done very similar selections. They were trying to find AGN. And interestingly, in this sample, and we exclude them from most of our analysis for which it would make things weird, we have, I forget, 4, 6, we have a few AGN, but it turns out it's also terrible at selecting AGN, this cut. Which is also funny, right? Because you might think like, okay, if I've got star formation happening a bunch, there's a lot of energy at the center, but it's not so much as happening in the disk, like surely that could be a good place for an AGN. Also, no, I don't know. They're very, very frustrating. But it helps us learn. So it turns out, because these are SDSS galaxies, a bunch of them got looped into MANGA. So we didn't ask for them to get observed. MANGA picked 10,000 galaxies to target with an integral field unit. So this means that within this section, there's somewhere between 19 and roughly 100 fibers to give us resolved spectra, spatially resolved spectra of each of these galaxies. So 14 of 126 of them. And this is done by my graduate student, Miles McKay. And the paper is in process. I have a draft. We are working on it. And so here you can just see that because they're at different redshifts, and because the bundles can be different sizes, different numbers of fibers, for some of them, the bundle's really picking up like the whole galaxy. Not the whole galaxy, there's probably some gas out here, but of the optically detected part, a pretty significant chunk. And for some of the smaller galaxies, this is a merger remnant. I don't know if you can see it, but there's definitely like all of these cool streamers. Other people also noticed it was a merger. And here they're only looking at that central region. So like everything happening out here doesn't get picked up by MANGA. Here's another example of that. So there's a few where, some of them, most of the galaxy is contained. And for some of them, maybe not as much of the outer region as we might hope, but still we're able to really now start thinking radially about what's happening in these galaxies. This is just an example of some of the different things we're saying. Encouragingly, I appreciate how careful Miles was. He kind of remade all my plots, was like, maybe they're not real. And I was like, well, I'm glad it turned out they were. They're still real. So this is the 2D stellar mass surface density, and this is the star formation surface density. And so they're color coded kind of with reddish and bluish as they should be. And so it's, you can see that we have, in terms of stellar mass, you have kind of these densities, lower density on the outside, higher on the inside. And with star formation surface density as well, we're seeing kind of those bluer cores. Again, these match the images. They're all lined up. These plots are shenanigans, but they're really growing on me a lot. You just have to like relax into them and it will be okay. So the reason this is exciting, so I'll tell you what you're looking at or what to look for, and you can decide. So the colors are bananas though. So the Breakbird galaxies are this kind of pinkish magenta line. The comparison star formation sample is blue. And the comparison quiescent galaxy is brown, or galaxies are brown. So the comparison sample is drawn. So of course, some of our parent sample also is in manga that are not breakbirds. And so Miles is using those as comparators to see when we look radially at different quantities, how do they go, right? Do we look more like the quiescent versions, or do we look like the star forming? So this is, I think, exciting and fun. These are really just two different ways of looking at the radius. Here is center of the galaxy, here is the outside of the galaxy. And so what we see, and in this case, this is for DN 4000, so our star formation, maybe unsurprisingly, the individual galaxies are the thin lines, and then the medians are and they're a little frequency weighted, so it's not exactly just the median, but it's pretty close. So here are our star formers, here are our quiescent galaxies, and here are the breakbirds. So at the center, they look a lot like our star-forming galaxies. And as we move to the outer regions, they look very much like they don't quite meet, but they look a lot like our quiescent galaxies. Now, not to be too excited, because I sort of like that shape, I will point out the breakbirds are a little all over the place, right? Those kind of thin magenta lines are much more spread out than we see, for example, for the quiescent. And the star formers also cover a fair range. But in average, we see kind of this very significant change here. We can also do this for looking at the surface density of the star formation. And again, so you can see here the probability density. So we're getting a lot of overlap between the star formers and the breakbirds, although it is not identical. And again, we see kind of, when we look at the median for the star formers and we look at the median for the quiescent galaxies, we see again some of this transition, regardless of how you figure out the radius, if you kind of use an ellipse or if you use the R effective ratio. So we're still playing around with this, but I think, we're starting to make an argument that maybe these galaxies are, at least many of them, transitional and quenching from the outside. My postdoc, who actually just started a job at Space Telescope, David Stark, is working on a paper about the gas in these galaxies. Again, sort of riding the manga wave. Some of them are in H1 manga. We also had at least some early data because some of them were observed with the Alfalfa survey, but the Alfalfa survey is not particularly deep. And so for the ones that were detected, there was a deficiency of H1 gas. So we were like, okay, it seems like something might be going on with the H1. And so here you can see that the comparison, so David drew from kind of H1 manga doing mass matching. So those are kind of the gold dots, where the breakbirds are blue. And in general, they have lower average gas content compared to the star-forming galaxies that we're comparing to. There are some kind of weird circles, which I'm not going to pull you into too deep, but just to say, the teal ones are counter-rotators, which is interesting, although I don't think particularly have a shape to them. And I don't know, is that green? These ones, the dark ones, have disturbed morphology. So there is some funny things going on, even in the ones that have H1. They seem to be disturbed. They seem that some interactions are probably part of why they're deficient. And if you look at the CDF, the cumulative distribution function here, you can see that it seems like they might be evolving off the main sequence. That this average lower gas content at the same mass. You can also see that here in histograms. We're sort of leaning towards the idea that something is disturbing them in such a way that they are moving away from the main sequence. They also have shorter H1 depletion times, as well as their gas phase metallicity is different from the control samples as well. And so again, we're kind of tiptoeing in the land of a little circumstantial, but our current favorite hypothesis is that perhaps this is because they're not having their gas adequately replenished, right? That their gas is being disturbed. Now it's possible that things could settle down again and the spiral could kind of reassert itself. But certainly the patterns we're seeing in the H1 are giving us implications that they really are depleted. We do have a program right now at GBT So for the galaxies that we don't have H1 masses, that we only have lower limits on, we have, it's actually really fun. So, we can just look at them and fill their crummy weather and just ask them to look at them for a really long time to see if we just needed lower limits, right? There's gas, just not that much, or if there's really hardly any H1. So we're trying to really improve those limitations to see how extreme the gas depletion might be. All right, the last thing I'm going to do in our last few minutes, I just wanted to share, I started a new class this quarter. It was called, well, it was kind of informal. The fun thing about new classes is they kind of form as they go, called Astronomy and Society. And so my hope with this class was to kind of, there's only so much you can do in 10 weeks, but my intention was to be able to improve our students' fluency in a wide range of kind of the history and philosophy of science and astrophysics, and kind of many of the community issues that have arisen over the last bunch of years, to give our students the tools going forward to kind of be able to join in those conversations and kind of develop their own ethical framework as scientists. So this is like a excerpts from my syllabus, from what we worked on. So we talked about kind of who are scientists, what does it mean to consider yourself a scientist, and who gets to decide that. So we did some talking about kind of science identities, and recent research about kind of what that means and how that means we interact in our communities, both in work and our home communities. We talked some about colonialism in astronomy. We looked at ground-based telescope sites, all the way from what happened in the American Southwest, in Chile, as well as what's happening at Mauna Kea. We looked at past community climate work. So a great deal of work has been done even in the small field of astronomy, including the Baltimore Charter, which talks about gender discrimination from the 90s, as well as the national recommendations from 2015 from the Inclusive Astronomy meeting. We also looked into, there's a great deal of reporting. So one of the interesting things about these topics is, people act like things are unknowable or we like have to figure them out from first principles, but a lot of work has been done over the decades. And so we looked into some of our reports on harassment that have come from the American Physical Society, from AIP, as well as from the national academies, on the climate for queer scientists, looking at gendered and racial harassment as well. We also tried to focus on how we make a difference. So we talked about tools for building resilient and healthy communities, for kind of bringing different pieces of ourselves to our work and what that looked like. We did practice reading decadal reports because everyone needs to practice reading decadal reports. And we got a chance to talk about land grants and land grab universities and kind of where the resources of our universities and our fields kind of came from. And I just wanted to share, I had them do a final project. So they worked on, we sort of practiced some of the skills we don't practice that much. We did reflective writing, we did some, conversations and debate, and they each got to pick a final project topic. Some of them are presentations, some are podcasts. And so these were some of the topics they came up with. So one of my students wrote on astrophysics in the military industrial complex and sort of the back and forth we have with the military industry in particular. One student wrote about speculative science fiction and world building by Black authors as scientific inspiration and sort of how those speculative fiction stories can inform the work that we do and how for her that was an important part of her scientific practice. One student is working on different models of accountability. So how do we, we look at these studies, we see what might be happening in our communities, but how do we close that loop? How do we go from like, oh, this should be different to like, how do we actually do that in a way that is functional? And one student is working on the climate impact of things like our computers as well as our computer resources, kind of the climate and material impact. So kind of how do we live at a time when people get computers every few years and then they disappear to go contaminate some new sites. So anyway, so it's been really fun. It went better than I could have imagined. I taught a mixed undergrad, the upper division undergrad and graduate class. And so I'm happy to talk about that more. I've been pulling together resources as well that I'm happy to share. All right, so a quick what's next. We are proposing a CubeSat called Miratus. This is to image the CGM in the far ultraviolet. I'm collaborating with a bunch of people. You can read them here. Many folks you might expect in ultraviolet astronomy as well as CGM. and working with my aeronautics and astronautics department. I'm happy to go more into the details of the many projects we have here that we're going to do with this tiny bread box of a science box. But the idea is to combine CubeSat technology that's pretty well proven and to make a 6U FUV narrowband imager. Its job will be to stare in places where we know that there is CGM. So in particular, Jess Work, who is my friend and collaborator at UW, was deeply involved with the COS Halo study. So this has done a ton of quasar absorption measurements. So we know that there's CGM there, and we know what it looks like. We know its metallicity, we know its temperatures. And so we also have now much improved predictions because we have so much observational data. We have constraints from my dissertation Fireball, although 2010 is basically 1,000 years ago in CGM science. So the idea is to try and really map that two-dimensional structure, so not just to get these pencil beams. We're targeting oxygen-6 at a redshift of 0.3, where we already know it should exist. And I'll point out, very early on, I was like, is it chunky? Is it smooth? What's the CGM look like? Certainly, the suggestions from the simulations are that it is hella chunky. And so this idea that we have these smooth halos is not probably what we expect to see. And so being able to actually map this rather than have a pencil beam is really important for understanding what processes are the ones that are dominant here. So again, this is a local simulation that we have run, and you can see kind of the difference between an edge-on or face-on galaxy. We're using, the instrument itself is very wide field. We're aiming for 20 arc minutes. Multi-filter, we're using a microchannel plate. This is useful because microchannel plates, unlike CCDs, don't need to be read out over and over again. So you just have time-tagged electrons, which makes it much easier to reconstruct the field as well. There's proven flight heritage here. Again, that time tagging, one of the hard things with CubeSats is to point to get good spatial resolution for astronomy targets. So the microchannel plate really helps us with that, as well as its low background noise. One of the things we are testing, we're working with JPL to develop some test filters, but we have a fallback with a commercial notch filter. And so we have several things in place to try measurements. We're building a lab right now to make measurements on these samples to see what will work for narrow band. There's plenty of contamination, so you have to be a little bit clever in your band design. And so again, the challenge is, of course, suppressing or identifying the background. It's relatively low signal. The CGM is not bright. We'll just keep getting better at it, I guess. And of course, the possibility of signal confusion. I will not make you read the science traceability matrix, but let me just tell you, it's excellent. Very motivated. So there's a lot going on. We're going to keep improving our LAE sample. In particular, I'm really excited about us starting to really do the modeling of the different components. So we'll really be able to separate what we think is happening from the galaxy and what might be happening in a truly extended way. With the breakbirds, we're going to try, depending on how fast I can write this Hubble proposal, we have 10 of them that have quasar lines of sight. And so we're going to do some kind of modified pencil beam surveys to see if we can see anything from CGM, something like 150 kiloparsecs away from these disks. Again, they're face on, so we'll see. And then we're going to build Miratus and map the CGM because that's the thing we should do. All right, that's what I have for you. Let's see, did I give you a picture at the end? No, sorry, no good pictures, you guys. I let you down. Usually I put something ridiculous, but I wasn't that organized today. So thank you so much. I'm happy to take questions.
Thanks. So we have time for maybe a couple of quick questions. We'll start with folks who are here.
Thanks. That was a great talk. I had a few questions about the breakbird sample.
Yeah.
The first was about the selection criteria for trying to look at ram pressure strip galaxies. I was wondering if you tested that for, I think there's a pretty good catalog at this point of known ram pressure strip galaxies. So could you take like 30 galaxies from Virgo or Coma and 30 control samples and identify which is which using your criteria?
That's a great question. We did not do that. It would have been very clever. We could certainly check it now, although I think now I would probably take the bet that we suck at it. But you know, it would not be the criteria I would use, as we didn't seem to find them. It might be an interesting question to ask, though. I should ask Stephanie, because she loves RAM pressure scripting more than I do, really. I'm just like a tag along. It might be an interesting way to sort of back engineer and say, like, what could we ask instead to better catch them? Yeah.
I was wondering, because you said you failed to find RAM pressure strip galaxies, but it seemed like your sample was H1 depleted, had short H1 depletion times, and was quenched from outside in. So why do you think that they weren't?
That's
RAM
totally
pressure
fair.
stripped?
So what I would say is we failed to maybe only find RAM pressure stripped galaxies. My suspicion at this point is that probably we have at least 2 commingled samples that are looking the same, and that some of them are perhaps either more secular or merger-driven events that are doing something, and some of them are RAM pressure stripped. So I suspect we actually have done an okay job at finding RAM pressure stripping, but not exclusively. Yeah, so I think that's, I mean, certainly morphologically for many of them, it's not like they are roguish, you know, they're not overflowing with H1. Yeah, thanks.
Right. We have time for maybe one more question. There's an online question. In your LAE sample, why did you cut at 1.2 arc seconds? Why not include a smaller full width half maximum?
Oh, that's great. Yeah, so partially because we just wanted to make sure that we had an adequate sample at given sort of any given space. We don't get great seeing at HET. And so kind of having a clear cut there just gave us a more homogeneous sample. We can do some work with kind of those smaller, well, you know what? Actually, that's a lie. The fibers are basically that size. We can't do much better than that, actually. A little better. But it just sort of keeps it clean to have the cut there.
All right. Well, thank you. Well, thank you again for coming and giving this talk, and we really appreciate your visits.
Thank you all for coming out.
And thanks to all of you for coming out.
And everyone online.